Okay, so welcome to my talk. Unfortunately, we had some hiccups with the equipment, so apparently the slides will not be on the live stream now, but you can download them on the FOSDEM website, so I'm sorry for that. Welcome to my presentation. It's called an optimized GFDM software implementation for low latency. First, I want to have a few words on who I am, where I work. My name is Johannes Demo, and I work with the Department of Communications Engineering at the University of Bremen in Bremen, Germany. The German abbreviation is actually ANT. And there I work with Carsten Bockelmann, and professor there is Armin de Corsi. Our research group is mainly focused on wireless communications, so physical layer or MAC layer, and yeah, we do some signal processing in general too. So, why do we work on GFDM? If you look at state-of-the-art technologies for wireless communications, they're usually optimized for high, for high data rates like LTE, but they also have a quite high latency, and also they have low reliability. If you think of LTE again, they usually have a target frame error rate of 1 to the power of -1, so 10% packet loss. And well, also it's non-deterministic communications, and mostly you have FPGAs, or everything's implemented in an ASIC, and yeah, pretty much fixed. We work in a realm where we are looking at Industry 4.0 applications. There we have a whole different setup. If you think of communications, we usually require a latency of less than 1 millisecond. We have a very, very high reliability requirement. It's debatable if this figure is really useful, but anyways, we need to have a more reliable communication system. And also we know that this thing works in a deterministic way. So if you look at this example, those slides here, they just move around and they just periodically send up updates where they are, how fast they move, etc., etc. And they do this periodically, and they are all connected to the system, and they all expect an update every so and so often. And if they don't get an update every so and so often, the whole system will shut down. And well, that translates to your whole production will just shut down. That would be bad for your company. So you want to have a reliable communication system. And in the future, we want to have more flexibility, and we want to have a software implementation that is parameterizable. Why do we want to have that? Well, this is just one example, but systems might look totally different for different applications. So we want to have as much flexibility as we can have. So now what we're working on, we want to have a new wireless communication system. And there's a project called HyFlex. It's supported by the Federal Ministry of Education and Research in Germany. And it's all in this whole conglomerate of industrial radio. So that's where I work. A little outline of my presentation here. I'm going to first start with a more concise introduction of what I do. Then I will introduce generalized frequency division multiplexing, or GFDM, as you've already heard in the title. Then I will talk about our low latency SDR implementation, and finally there will be a conclusion. So let's start with the introduction. If we have a look at the system model for a communication system, on the file layer we usually have a source, we have some kind of forward error correction, and today I'm going to talk about the waveform. So that's the part I'm going to focus on today. And our requirements here are that we have it more flexible than before, that we want to have it robust, and we need to have favorable coexistent properties. Well, so a little bit further, I already said that we want to have latency of less than 1 millisecond. So if we look at this system now, we have a device that needs to send out status and receive an update within a millisecond. And in between, there's a communication system. So we'll have a channel here. We can control its properties by setting certain filter properties, etc., and the frequency, but in the end, well, we have to deal with it. But what we can completely control is our signal processing here, here, and here. And this is the one we want to have as an SDR implementation, and then we want to measure its latency so we can have first feeling of how good it will perform and what we have to expect from that implementation. Then finally, we want to answer the question, can we achieve low latency? So now to dive deeper into GFDM, I will introduce that. Well, back in the day, everyone used single carrier transmission. So you had a certain bandwidth, and you would just divide it over time into time slots. That's what we depicted here. So you would transmit n symbols, complex symbols in digital communications mostly, and you would send them out one after the other. As we increased data rate, that kind of involved a lot of problems like multipath propagation, and we needed more and more complex equalizers. So along came OFDM, which helps us solve a lot of problems here. And also, we got a lot more flexibility. Now, instead of dividing our resources in time, we just divide them in frequency. So we have low bandwidth subcarriers. Still, we can transmit n complex symbols at a time. GFDM wants to be more flexible here. So we can have a flexible scheme where we divide our resources, time and frequency, into subcarriers here and time slots. That's this direction. Okay, still we have n complex symbols that we can transmit on our n data symbols, but now it's more flexible. So how does the GFDM work? Just a quick introduction. First, we assume we have complex symbols, these Ds, and we want to map them to certain resources. So we go here to our resources, and we just map our Ds to these resources. And, well, we save that in a vector of size n, of course. And every single one of these elements in the vector now corresponds to one resource element here in our resource grid. If we for some reason don't want to use all the resources, we can just set them to 0, so it would look like we just don't transmit on that frequency. The next step will be to do modulation. Well, if you'll read through the papers, you'll see a modulation matrix A, and you just multiply it by D, and bam, you have your transmit signal. Well, how does A look like? For every resource, it contains a circularly shifted and modulated replica of a prototype filter. So the prototype filter does actually shape our signal, just like we would do with, for example, a single carrier transmission where we have a root raised cosine filter. And now we just shift it to the frequency and the time where we want to transmit a certain symbol. And that's what actually every entry of A does contain for every symbol we want to transmit in such a GFDM frame. And I mentioned OFDM earlier. Now, in contrast to OFDM, we do not use rectangular filters in time anymore. If you're familiar with OFDM, basically you have a rectangular filter over time, and that translates into a sync and frequency, and that's good, but we want to do better and tackle the problems that involve that. Last thing we do is we can still use a cyclic prefix, but we do only use one per frame instead of for every OFDM symbol in OFDM. So we might be more efficient there. Why do we want to have a cyclic prefix? Well, this also translates to a circular frame property, and that again in terms translates to a more simple equalization technology. So we have simpler equalization if we use a cyclic prefix, hopefully. So we want to have that, and it's great that we can have that with GFDM too. Okay, so there's one challenge. I told you the A is just a matrix, and this matrix might be quite large, so this multiplication is very inefficient, and we want to improve on that. Just to give you a quick overview, we want to modulate that again, but now we want to do that in the frequency domain. We choose our subcarrier filters such that they are shaped like this. So we'll only have non-zero elements for our subcarrier and some area around it. And now we can implement that with a fast Fourier transformation. Okay, that also involves a few more things. So the first thing is we will always have interference with neighboring subcarriers. You can see they overlap, but we can manage this interference because with our filter design, we are now in charge of this interference, and we can actually later on in the receiver, we can cancel that out. And this design then translates to a more robust implementation if you think of imperfections like frequency offsets and timing offsets. So a system where we actually have a more well-localized filter for our subcarriers will be more robust against this kind of imperfections. Okay, so let's move on to our low latency SDR implementation. I didn't need to have to start from scratch. When I started to look at GFDM, I looked around if I could find any previous works, and I did. Thanks, Andre. He already started GFDM, and well, I took that up and implemented all the things I needed and worked on code optimization. I added quite a few tests so we could improve on code here. And now the system has a few components, so we can do modulation, we can do demodulation. We'll also have a synchronization part, and we can have this mapper and demapper. Okay. A little bit on our, well, software structure. If you work in academia, you often have, well, look at single frames, and you do quite a bit of offline processing for your simulations. So you want to have an interface to use with Python, to use it with NumPy and SciPy, or some other unnamed software. And also, this is quite nice to play around and just get a feeling for how things work. Here we want to have an interface, a simple interface, so we can just do that. And then we want to have our implementation, which is very modular, it's optimized, and again, it should have a simple, just C++ interface where you just push around your pointers. And then on the other hand, you can just plug that into GNU Radio, so you can just plug that into your block structure, just call the appropriate functions, pass around the pointers, and yeah, just use all the benefits of GNU Radio, like it takes care that everything runs fast, that it runs multi-threaded, that you have your hardware interfaces, you don't have to worry about that. I mean, no one wants to rewrite any drivers or things like that. So that's the general idea of how we split our software into different components. The last part, I want to actually show you some benchmarks of the different parts of our system. First off, for this benchmark setup, I made a few assumptions. So we would also always look at the perfect channel, so there's no noise or, well, actually no channel. Wouldn't make sense for performance evaluations, but for benchmarks, it works fine. Then also, for the kind of communication systems I'm looking at, we always have small packets. It's debatable if 1024-bit is still a small packet, but that's up to, well, the people involved in every project. Then also we always look at small constellations like QPSK. We won't go up to like 54 QEM. In order to understand the simulations a bit better, you need to have to know about two parameters: n, the block size of our GFDM frame, and j, it's the amount of interference cancellations iterations. Earlier I mentioned that we will have managed interference between different subcarriers. Well, we allowed that in the first place, so now we need to cancel that out in a smart way. And then we want to identify which parts of our system are actually taking up the most time, and which parameters need to be chosen carefully such that the system does not, well, exhibit bad performance, like the latency will go up quite tremendously, or the throughput will just decrease up to the point where it's not usable anymore for us. Okay, so let's first look at the transmit side. We have three parts. We have a mapper, we have a modulator, and we have a cyclic prefix addition. And as you can see, resource mapping and cyclic prefix addition just don't play a role here. They are less than 1 or 2 microseconds for every frame. So the interesting part is actually the modulator. And you can see that for two parameter settings. I chose 128 or 64 subcarriers here. And then you just vary the number of time slots you have. You might wonder, why don't we just choose powers of 2 for our modulation? Well, if you look at literature again, you'll see that you can't actually use GFDM with integer powers in time and frequency at the same time. So we end up with this kind of weird values here. And that also brings us to the reason why this is not just linearly increasing. But if we have a look at, well, the FOSDem implementation that does the Fourier transforms for us, if we have small prime factors, for example here, if you look at these values, this value, that's the dot here, we have small prime factors, so our Fourier transform can be implemented quite efficiently and it's quite fast. If we have a look at this value here, so that's that dot here, we have quite large prime factors. 19 is already large here. So our implementation will increase in terms of latency. So we need to choose our parameters here very carefully. Okay, so now we know that. On the other side, on the receiver side, we first start with synchronization. Since we have a system where we expect quite high SNRs, like 10 dBs or something, we will always start with energy detection, which is quite fast, and then just search for the correct symbol start or frame start in a certain window. And now here you can see that depending on the number of subcarriers, our implementation increases in terms of latency here. So one frame, we want to just synchronize, find the correct position of our frame, and depending on the number of subcarriers, this might take like 18 microseconds or over 40. Okay. Next up, the most important part, the demodulation. Here you can see that, again, we have this behavior due to prime factors here in our Fourier transform. So we should, again, choose our values here wisely, but also we can see if you need to do more interference cancellation, of course that will add up to our latency as well, but actually not too much. It's not like we can't afford a few iterations of interference cancellation without going over our latency budget. So that's already almost it. I want to come to my conclusion. Here we have a look at the overall latency budget of a system that we designed for two different numbers of subcarriers. And here I just brought a little example. So if you think back, we have 64 subcarriers, we have 21 time slots. So that translates to 1,344 complex symbols we could possibly squeeze into one Gfdm frame. And if we now think of it, we run at 20 megasamples per second, so we occupy like 20 megahertz of bandwidth. We have an airtime of roughly 74 microseconds. We then add another one-way processing delay of 92 microseconds. So if we just go from transmitter to receiver, latency will be around roughly around 166 microseconds. And then in the end, and if we think back of this circle in the beginning, our round trip time will be in the, well, somewhere in that range, so 330 microseconds. So that's what we need to expect from such a system. And that in terms just proves the point that we can actually do a low latency SDR implementation with the radio. And thanks for your attention. There's maybe time for one question or so. Yeah.
It is also increase the reliability of the transmission, because you said there were two things: the latency and the reliability that you wanted to improve.
Yeah. Here, yeah. So, do we also improve reliability? That was the question. Or in this work, we only looked at at latency, but if you think back of how I talked about imperfections of our channel, for example, if we have offsets that we might not be able to compensate for, then Gfdm would also show quite favorable figures in terms of reliability. Yeah. Yes. Yeah, that's a good question. So, okay, keep it quick. Why would I want to have an SDR in an Industry 4.0 application? Well, we want to have it as flexible as possible, so we can just play around with our parameters and everything. And I think that doing everything in software is just the easier way to go. It's just more flexible, it's faster to implement and everything. if you start to implement it on FPGAs, you open up just so many more questions that you have to answer besides all the other algorithms. So that's the reason for it.
Thank you, Ron.